Hi guys, so this video is supposed to help with lab 3 analysis, specifically for task 1, where for task 1 you were supposed to set 2 of the forces on a force table at different angles from each other with different masses hanging from each other, and use a third force to create equilibrium. And you know it's an equilibrium when the ring is in the center, because that's when you know all the forces are canceled out. And so for analysis, we want to find percent error of the equilibrium force, the magnitude, so how much weight it is in newtons, and also the direction in degrees, right? So let's say this is my sample data, right? I'm making this up. Your data is obviously not going to be exactly mine because you had a lot of choice in it. Let's say I hung 200 grams from my first one, and again, this 200 grams includes the mass of the mass hanger, right? The mass hanger has 100 grams on its own, and then 350 grams for the second one, and I hung the first one at 30 degrees and the second one at 70 degrees, right? So we want to fill in the rest of this table. Mass in kilograms, you've done this before, divide this by 1,000. And I can just drag it down to do the same calculation for this guy. And for the weight, sorry, in newtons, multiply this by 9.81. You've done this before as well. So the unfortunate thing is that Google Sheets only works with radians, but of course we talk in degrees. So, but the nice thing is that they have some kind of function here that can convert degrees to radians really easily, and it's equals radians, open parentheses, and you click on the angle you want, which is 30 in this case. So 0.52359 blah, blah, blah radians is the same thing as 30 degrees. Right? It's just a different way of expressing an angle value. And I'm going to drag this down so it does the same calculation for my 70 degrees. Right? So 1.22 radians is the same thing as 70 degrees. Okay, so let's say my third force, which is supposed to be equilibrium force, I moved it around. I found that 490 grams worked perfectly, and 235 degrees worked perfectly. Okay, so my mass, same as before, so I can just drag, because these are all the same calculations, right? I can just drag down from the top, because it's the same exact stuff, and this is all of it. This is my entire table filled out. Now what we want to do for this video is to figure out how to find the accepted values. And we're going to do it by a way called component method, right? So to understand this, we need to, I'm going to draw some stuff on paint. Be prepared because I'm not a good mouse drawer. Okay, so just to copy over some stuff. Force 1 was 1.962 newtons at 30 degrees. Force 2 was 3.435 newtons at 70 degrees. And we want to find the equilibrium force, right? To understand how we're doing this by component method is force 1, if we drew this to scale or a quick sketch of it, it looks maybe something like that, right? Where the magnitude of this is 1.962 newtons. And the direction from the horizontal, this angle right here, is 30 degrees, right? Now we've learned in class how to break this into components. And to break into components, it's your horizontal component, which is how much horizontal it is. I'm going to make this a different color. How much horizontal it is. And also how much vertical it is. Right? So there's a horizontal component and vertical component. And we've used equations on how to find these, right? Where if you have a vector A sub x, I can't do subscripts here on paint, but A sub x is equal to A times cosine of theta. And A sub y is A times sine of theta, as long as your theta is measured from the positive x direction. Right? In this case, my 30 degrees is measured from the positive x direction, right? To the right is a positive x direction. So to find this horizontal component, I'm just doing A, which in this case is 1.962 newtons, times cosine of my 30 degrees. And a vertical component is A times sine of this, right? So if I do this, let's do some math over here. So let's say this is all F1 components. So F1x is equal to, I'm gonna make this look a little bit better by merging it and centering it like this. Okay. F1x is equal to my F1 times, and if you want to use cosine, it's just regular cosine, like that. Cosine of your angle in radians, right? Because Google Sheets only works in radians. And so horizontal component is this. F1y is this times sine of the angle in radians, right? So this is saying that instead of thinking of this one single force of 1.962 newtons at 30 degrees, you can think of it breaking into components as a horizontal force of 1.699 newtons to the right, and also 0.981 newtons vertically up. That's essentially what this is saying. So these are the components for F1, and we also want to do the exact same thing for F2. Now, the reason why is because when we add all of our vectors, we can only add if they're in the same direction, right? Because we're going to add the components of F1 and F2 together because we want to see the total effect of these two forces on my ring. Okay, so if you want to do F2 components, same exact math here, right? F2x, F2y. And I'm going to merge these two and center it so it looks a little nicer, equals the force of F2, which is this guy, times cosine of the angle in radians. And for this guy, same thing, times sine of the angle in radians. Yes, okay, same things. Okay, great. So these are the x components and y components of F2. And it makes sense that they're both positive because this is at 70 degrees, and 70 degrees is upper right, right? I should actually have vector heads on this, but upright, where x and y values are positive, and same with the 30 degrees, right? They're in the first quadrant. So this is saying that the horizontal component of this from here to here is 1.17, and the vertical component this is 3.226, right? So if we add all this stuff together, so F total, right? F total components. FT, I'll do FNet, FNet X, and FNet Y is equal to, I add these two, right? So I can do equals sum, which you're adding these two values. I want to add this guy, comma, and this guy, and close parentheses. And do the same thing with the Y direction, right? You can only add vectors numerically, just adding them, if they're in the same direction. So these are both in the Y direction. So I want to add this guy and this guy. This is going to tell me how much total horizontal it went and how much total vertical it is, right? The forces, right? So we're adding this horizontal piece with this horizontal piece, this vertical piece with this vertical piece. So we see in total how much horizontal and how much vertical the force is based on these two forces. So this is the components. So if you want to find the actual value, we need to use Pythagorean theorem, right? Because in total, we have a total net force of 2.86 newtons to the right. So this value here is 2.87, I would say, newtons. And we're going to have to do a second video because there's only 20 seconds left. To the right, and 4.2 upwards. This is obviously not the scale. Upwards, right? And I want to really want to